Let's work with the next question, guys. It says show that the vector A and vector B are collinear vectors. Collinear vectors simply, if at all they are in the same line, that's what I say, or they are in the parallel line. Now let's talk about this in the visual graphic diagram a little later. Right now, mathematically, if I can show that vector B can be written as lambda times vector A, then I can say these two guys are basically collinear. Or we can also say that if A1 by B1 is equal to A2 by B2 is equal to A3 by B3. That means if the direction ratios are proportional, or that is equal to basically a constant called lambda, then I can say one of these guys would actually prove it mathematically that they are collinear vectors. Now let's do that, and we'll go back to the graphic diagram a little later. Look at that. Can I write vector B or vector A in terms of this? I can. Let me write vector B right now, which is negative 4i plus 6j minus 8k. I can see that there's something in common in this, right? I can write this to be, I can take just 2 common out. I can get minus 2i plus 3j minus 4k. Makes sense. Is this guy looking like vector A? Not exactly, because you have a signs difference, so I think I should take a negative sign also outside. I get a negative 2 outside. You get a 2i minus 3j plus 4k. Now, is this looking like vector A? Of course. Then I can write negative 2 times vector A, and I started with vector B. So this was vector B for me. I could actually write vector B in terms of lambda times vector A, where lambda is negative 2. Now I can say yes, vector A and B are basically collinear. Otherwise, I would try to do this. It means I would divide these two guys, find the ratios of 2 over negative 4. And would that be equal to negative 3 over 6? And should that be equal to 4 over negative 8? See what I'm getting? I can get a negative 1 over 2 here. I get negative 1 over 2 here and negative 1 over 2 here. It means they're all equal to some constant, and if that is happening, also mathematically I do say that vector A and vector B are basically collinear. Now let's visualize the same problem in the three-dimensional space. I can see that there are 2 vectors in this case. Now these are my 2 vectors, okay? I'm taking the exact vectors, that is 2i minus 3j plus 4k, which is my first vector here. All right, and the other one is nothing but minus 4i. Look at that, minus 4i plus 6j minus 8k. These are the 2 vectors, and they are in space. Are they collinear? They're actually not collinear, but they are parallel for sure, and they have the same direction. Now, what if I move these guys? These guys are free vectors. If you need to understand what are collinear vectors and what are free vectors, you need to go back to a section in the same application where I've discussed this in detail. That will actually make you understand why I can move these vectors and it still remains the same thing. Okay, its direction cosine or direction ratios and direction cosines would not change if I move this vector in space like this. So let me move this guy, and I'm just keeping it here. Now look at that. Do you think so they are collinear? Yes, they do form a single line. They are in the same line. So I can very clearly say that these 2 guys are collinear. When can this happen? It can happen only in these 2 conditions. If I can represent one of the vectors as a lambda times the other vector, which I can do it here, or I can actually do that if I can find the direction ratios, and they should be equal to what? They should be equal to some constant called k. That's it.